Welcome back, class, to the last module of Module 4, that is Module 4.6, Electrolysis. Today is 25th September 2023. I still remain Professor Engineer JC Igwe. We'll look at introduction, a brief introduction to electrolysis, Ohm's law, Faraday's law of electrolysis, electrolytic cells, examples of electrolytic cells, comparison of electrolytic cell versus galvanic cell, illustrations, and conclusion. Introduction. Now, an electric current may be conducted by 1. Metals, in which case no chemical change is noticed, although physical changes such as heating or magnetic effect may result, and this is what we call metallic conduction. 2. Electric currents can result from solution of electrolytes. These solutions conduct an electric current are decomposed by it. This type of conduction is called electrolytic conduction, and that is what we are interested in. In the electrolytic cell, the current is led into and out of the solution by electrodes. The positive electrode is the anode, and the negative electrode is the cathode. Now, the flow of electron round the circuits by the battery constitutes the current. The cathode supplies electrons to the ions in the solution, while the anode accepts the electrons from the ions in solution. Positively charged ions, that is cations, are attracted to the cathode, while negatively charged ions, the anions, travel towards the anode. As the current flows, electrons are lost by the cathode and are released to the anode as a result of the discharge of ions. Thus, decomposition or electrolysis takes place, and this whole assembly constitutes an electrolytic cell. Ohm's law. The current passing in the external circuit is directly proportional to the EMF and inversely proportional to the resistance. That is what Ohm's law says. The ampere, that is 1 ampere, is equal to a flow of charge at the rate of 1 coulomb per second. So when one current is flowing, that is equal to flow of charge at the rate of 1 coulomb per second. When electrical energy is converted into heat energy by measuring the heat production in the resistance wire, it is found that the heat produced is proportional to the EMF in the circuit and quantity of electricity passing it. Of course, we'll still see this in Faraday's laws. So electrical energy is E multiplied by I, which is the current, multiplied by T. So remember, unit of electrical energy, we made that at the beginning, volts times coulomb, which is equal to 1 joule. So which means the current is measured in amperes, while the quantity of electricity passed is measured in coulombs, C. So 1 coulomb is the quantity of electricity passed. 1 ampere flows in 1 second. Thus, quantity of electricity Q is current times time, equation 3. We met all this before, that's why I'm moving a little fast. Faraday's laws of electrolysis. The first law states that the weight of an individual substance liberated during electrolysis is proportional to the quantity of electricity which passes through the electrolyte. That is, weight is proportional to Q, where Q is current times time. The second law states that the weight of various substances liberated by the passage of the same quantity of electricity through different electrolytes is proportional to the chemical equivalent of the ion. So weight liberated, E, is equal to weight of 1 mole divided by charge carried by the ion. So examples of electrochemical equivalent, for instance, for chlorine, weight of 1 mole, 35.46 divided by 1. Barium, 137.4 divided by 2, the charge is 2. Sulfate, the charge is also 2. Therefore, we have weight liberated is equal to a constant multiplied by E multiplied by I multiplied by T. And by experiment, this constant is equal to 1 over 96500. That is the coulombs. Therefore, we have weight liberated equal to E multiplied by I multiplied by T all over 96500. And that is equal to Z multiplied by I multiplied by T, where Z is equal to E over F. Electrolytic cells. Remember, we made a difference when we defined electrochemical reaction into galvanic cells or electrochemical cells and electrolytic cells. So voltaic cells use a spontaneous chemical reaction to drive an electric current, that's electrochemical cell, through an external circuit. These cells are important because they are the basis of the batteries that fuel modern society. We've said that. It is also possible to construct a cell that does work on chemical system by driving an electric current through the system. So this is now in the opposite direction. These cells are called electrolytic cells. In electrolytic cells, electrical energy is used to carry out non-spontaneous reactions. So you see the opposite. In electrochemical cells, spontaneous reactions are used to generate electrical energy. In electrolytic cells, electrical energy is used to carry out non-spontaneous chemical reactions. So we can say a chemical energy is transformed into electrical energy in electrochemical cells, while in electrolytic cell, electrical energy is converted to chemical energy. So which means electrolysis is used to drive an oxidation reduction reaction in different direction in which it does not spontaneously take place. Examples of electrolytic cells: molten sodium chloride, electrolysis of aqueous sodium chloride, electrolysis of water. These are specific examples. If you Google them, you just see some summary where you can look at what is happening at each of the electrodes. But let's take in the case of molten sodium chloride. Sodium plus, which is positive, migrates to the negative electrode, and chlorine minus, which is negative, migrates to the positive electrode. When sodium ion collide with the negative electrode, the battery carries a large enough potential to force these ions to pick up electrons to form sodium metal. You see the equation Na plus plus E will give us sodium metal. Chlorine ions collide with a positive electrode are oxidized to chlorine gas, which bubbles off at this electrode. We see the equation Cl minus giving us Cl2 plus 2 electrons. Now the net effect of passing an electric current through the molten salt is to decompose sodium chloride into its elements, sodium metal and chlorine gas. And the equation is there. What happens at the cathode and what happens at the anode. The potential required to oxidize chlorine ions to chlorine gas is 1.36 volts, and the potential needed to reduce sodium ions to sodium metal is minus 2.71 volts. Therefore, the battery used for this reaction must therefore have a potential of at least 4.07 volts. This example explains why the process is called electrolysis. That is, means using electric current to split a compound into its elements. Electro, then lysis means splitting, so electrolysis. Electrical energy is used to force non-spontaneous chemical reaction to occur. Two examples of commercial electrolytic reactions are electroplating of jewelries and auto parts, electrolysis of chemical compounds. And electrolytic cells consists of something like we had in that galvanic cell, a container for the reaction mixture, two electrodes, a mass in the reaction mixture, and then a source of direct current. That's what is makes up electrolytic cells. Now we'll compare electrolytic cell versus galvanic cell. We're using this table: electrolytic cell, galvanic cell. Of course, you know that galvanic cell is an example of electrochemical cell. The first one, electrical energy is transformed into chemical energy in the electrolytic cell, while chemical energy is transformed into electrical energy in the galvanic cell. Anode is positive electrode and cathode is negative electrode. The galvanic cell, anode is negative electrode and cathode is positive electrode. For electrolytic cells, ions are discharged on both electrode and cathode. Ions are discharged only on the cathode for galvanic cells, and so on. So you can see we'll try to differentiate that using that table there. An illustration to calculate the mass of silver deposited when a current of 2.6 ampere is passed through solution of silver salt 70 minutes. You can see that it's a very simple one: quantity of electricity, current times time. That's what you have there. Then the equation is there. The weight of silver, 1 Faraday, that's 1 electron, is passed. And we'll do the calculation and arrive at 12.22 grams of silver deposited. Thank you so very much. We've come to end of module 4.6, and of course the end of module 4. Here we've looked at Ohm's law, Faraday's laws of electrolysis, electrolytic cells. Then we'll compare the electrolytic cell with galvanic or electrochemical cells. Now we'll give you a little time, maybe a day or a day gap or anything, and we'll go ahead and continue with the last module for the class, that is module 5. Thank you very much for your time and for listening, and we hope you enjoy all the classes and it makes it a lot easier for us. Thank you and God bless you.